We begin with polar covalent bonds. We've already done what a non-polar covalent bond is. Now we take up the polar covalent bond. A polar covalent bond gets formed between two atoms which differ in their electronegativities. Take for example something like HCl. In HCl, chlorine is more electronegative, hydrogen is less electronegative. Therefore, the electrons which are shared in between the two, right, the electron pair which is shared between chlorine and hydrogen, it remains more towards chlorine, which we show by putting an arrow like this. And therefore, chlorine gets a partial negative charge, hydrogen gets a partial positive charge, and the bond which is formed in between them, the covalent bond, that is precisely called a polar covalent bond. You can have many such examples. You can have ammonia, in which nitrogen is more electronegative, and the electron pairs of the covalent bonds formed between nitrogen and hydrogen would remain more towards nitrogen. Now, the point is, if we talk about a polar covalent bond, what do you think should be an extreme case of polar covalent bond? Which means, if you have a polar covalent bond, what would be the extreme case? Here, if you take up H and Cl, right, there's a polar covalent bond in between them. What would be an extreme case of that polar covalent bond? The extreme case would be the electrons of the covalent bond going right towards chlorine and remaining towards chlorine, or the extreme case would be donation of electrons to chlorine by hydrogen. What would that be called? It would be an ionic bond. So here, you just have to know that ionic bond is the extreme case of polar covalent, right? In general, any polar covalent bond will have some ionic character in it. It may not be a complete ionic bond, right? But there will be some ionic character in it. The amount of ionic character in any polar covalent bond determines the magnitude of polarity in that bond. So it is very important for us to evaluate the ionic character of any polar covalent bond. Many equations have been given for evaluating the percentage ionic character of polar covalent bonds. However, one of the equations which we can use is the Pauline's equation. The Pauline's equation says that percentage ionic character of any polar covalent bond is given as 18 into Xa minus Xb raised to 1.4. What are X's and Xb's? Right? Here we can say that where Xa minus Xb is the electronegativity difference between the two atoms sharing that covalent bond, right? So Xa minus Xb is the electronegativity difference, right, between the two atoms sharing this polar covalent bond. So this is one equation which can be used for knowing the percentage ionic character of any polar covalent bond. You can also measure the magnitude of polarity, or you can get an idea about the percentage ionic character of any polar covalent bond by measuring a physical quantity called dipole moment. So, one more way in which you can get an idea about the magnitude of polarity of any polar covalent bond, or the amount of ionic character a polar covalent bond would have in it, right? That can be known by measuring this physical quantity called dipole moment. So let us now find out what dipole moment is. So dipole moment is a physical quantity which is denoted by nu. It is denoted by nu, and the value of nu can be found by this equation: nu is equal to q into d. So dipole moment is a physical quantity which can be calculated for any polar covalent bond between two atoms using this equation q into d. But then what is q and what is d? Q is equal to charge on any one of the atoms between which polar covalent bond is formed. This Q, which is a charge on any one of the atoms in charge on any one of the atoms between which the polar covalent bond gets formed. This Q is measured in ESU. ESU is one of the units which can be used for measuring charge. We say it is measured in ESU. What is ESU? ESU is electrostatic unit. Electrostatic unit, and you know that charge any charge of an electron or a proton is 1 into 10 is to minus 19 coulombs, right? In terms of ESU, it is 4.8 into 10 is to minus 10 ESU, right? So magnitude of unit charge is equal to 4.8 into 10 raised to minus 10 ESU, right? Which in terms of coulombs can be 1 into 10 raised to minus 19 coulombs, kind of, right? So so this is about Q. How do we measure Q, and in what units we measure Q? Now we take up D. What is D? D is equal to distance between the centers of two atoms in terms of centimeters. So you have to get the distance between the centers of two atoms in terms of centimeters. So you have to use unit centimeters. Therefore, now we can very easily understand that unit of dipole moment will be equal to ESU dot centimeter, right? This unit, ESU centimeter, is also evaluated in terms of dBi. So one more unit which you can have for dipole moment is dBi, and we say that nu is also measured in dBi, capital D, and you know that 1 dBi is equal to 1 into 10 is to minus 18 ESU centimeters. This relationship you all have to know. So this is about how to measure the dipole moment, right? The point is, if you have only two atoms with a polar covalent bond in between, then this measuring dipole moment of that polar covalent bond will be very, very simple and easy. However, the problem comes when you have polyatomic molecules having more than one polar covalent bonds. Now here, for such a molecule which is polyatomic, having more than one polar covalent bonds in it, getting the dipole moment of the entire molecule or the molecule as a whole becomes very difficult. Why? Because dipole moment is a vector quantity, and therefore, in order to get the resultant dipole moment of the entire molecule, which is polyatomic, we will have to consider two important aspects. One, the resultant dipole moments or resultant bond moments of all the polar covalent bonds in the molecule will have to be considered. And two, their three-dimensional orientations. The three-dimensional arrangement of all the polar covalent bonds will also have to be considered. Why? Because dipole moment is a vector quantity. In fact, one can assume dipole moment to be a kind of force which has its direction from less electronegative atom towards more electronegative atom. So dipole moment basically is a kind of force having and it is a vector quantity. So the value of dipole moment depends also on the directions of the polar covalent bonds. So in case of polyatomic polyatomic molecules, the resultant dipole moment, right? Resultant dipole moment in polyatomic molecules can be found by knowing two important parameters. One, resultant bond moments of all the polar covalent bonds. Of the molecule. And two, the three-dimensional orientation of all these bonds. Why? Because the second property is very important. The second parameter is very important. The reason being, dipole moment is a vector quantity, and directions have to be considered for knowing the values of dipole moment. There are some very interesting examples, right? Some polyatomic molecules in which you find polar covalent bonds. So there are more than one polar covalent bonds in these molecules. However, the resultant dipole moment of the entire molecule as a whole is zero. So in spite of having polar covalent bonds, the resultant bond moment of the entire molecule comes out to be zero. Why? This is largely dependent on the orientations of these polar covalent bonds. Let us take up some examples where this can happen, right? We can take up examples like, BeCl2. Chlorines are more electronegative. The bond moments, they have to they have to be towards chlorine, right? The electron pairs remain more towards chlorine, and each chlorine would be partially negative, right? In this case, right, there are two polar covalent bonds in the molecule. However, the directions of both these polar covalent bonds is exactly opposite, and the magnitude is the same. the resultant dipole moment would be 0. Net dipole moment would be 0. You talk about something like BF3. You talk about something like BF3. In BF3, there are, uh, 3 polar covalent bonds. And these 3 polar covalent bonds have different directions. But you find that in BF3, the dipoles are moving towards fluorine, fluorine being more electronegative. Still, the resultant of any 2 dipoles can be obtained by using law of parallelogram of forces. You can use the law of parallelogram of forces for knowing the dipoles of these 2 bonds. The resultant dipole goes like this. The parallelogram, the resultant dipole is given by the diagonal. The resultant dipole of these 2 bonds, polar covalent bonds, is in downward direction, exactly opposite to the direction of this bond, and therefore the bond moments of these 2 would cancel out, and the net dipole moment is 0. So any planar trigonal molecule, right? Any planar trigonal molecule, right? You may have to get the bond moments of any 2 of the bonds, and you generally find that the resultant dipole is exactly opposite and more or less of same magnitude to the 3rd bond, and that is why the dipole moment becomes 0. You can see that dipole moment has become 0. You talk about something like methane, a molecule like methane. The dipoles, they go towards carbon, and the methane, the molecule itself, is like this. You have hydrogen, 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 carbon, and 1 more hydrogen here, right? Now, what would be the resultant of these 3 hydrogens? The resultant of these 3 hydrogens will be given by a dipole like this here, right? So we can put this as, the resultant dipole can be like this. This is the resultant dipole of these 3 going towards carbon, and this is, exactly opposite to the 4th bond, the moment of the 4th bond, and so the net dipole moment will become 0. In short, all symmetric molecules will have 0 dipole moment. Generally, will have 0 dipole moment. Clear? The same kind of thing you can find even in carbon tetrachloride, CCl4. Same thing would happen, right? So these are some of the molecules where, in spite of having polar covalent bonds, we find that the net dipole moment is 0. In general, if you have 2 polar covalent bonds, right? In general, if you have 2 polar covalent bonds having an angle theta in between them, right? The resultant dipole will be given as, see, let the bond moment of this be mu1 and this be mu2, right? So the resultant would be, under root mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Here it is very clear that if the value of theta decreases the bond moment, the resultant dipole moment would increase, right? And if theta increases, the resultant dipole moment would decrease. This can be very easily exemplified, right, by taking a simple example of dichlorobenzenes. There can be 3 different isomers for dichlorobenzene, right? You can have orthodichlorobenzene, you can have metadichlorobenzene, and you can have paradichlorobenzene, right? You can see that if you consider the theta, these are all polar bonds between carbon and chlorine, and the dipoles would be pointing towards chlorine. Now, if you have the bond moment here, which is given by which depends on the value of theta, right? So here you find that theta is less, and therefore dipole moment of orthodichlorobenzene would be more than metadichlorobenzene. Why? Because the theta is more, and this would be, greater than this. Here the two bond moments are exactly opposite in direction, and therefore this comes out to be 0 for this molecule. So this is about the dipole moments and how theta can affect the value of dipole moment, right? This is all about the polar covalent bonds. Now we take up the third category, coordinate covalent